There we go. All
This
right,
is
great. Next, we have Michele Levi talking about the high loop, high spin frontier.
okay. So first of all, hello, Zoomplituders across the globe. It's a very strange experience. Like joining all the others and thanking the organizers for being brave enough to still carry through, and in particular to the literally unprecedented Zoomganization by Anastasia. So thanks. Um, and first, I would like to start by saying that I'm just psyched to hear about all these new works that are done on spin today. I was very excited to hear about all this work, obviously on a topic which is very near and dear to me for some years now. And so, first of all, though, I would like to answer a basic question, and that is like, why do precision and gravity? And although for this community, probably precision computation is not a bad word, you'd be amazed how misunderstood and unappreciated it is in even near enough circles. So I'd like to highlight the following. So sure, I mean, there is like real world data and we're all excited. Gravitational waves have been detected and there is high demand on accurate theoretical gravitational waveform templates and all of the compelling motivations that you heard about today. But I'm personally very honored and happy to be in the service of LIGO people as much as I can. But in all honesty, my research on this topic has been driven by pure science questions. So particularly for me, I want to highlight the following. And these are the type of questions that I expect and actually I see that we answer by just doing precision computation in post-Newtonian gravity. So one, like how well can perturbative gravity theory capture strong gravity? So it's like it's a known phenomena that PN theory gives us accurate results even in regime where physically it shouldn't hold. So that's like a puzzle which doesn't have full understanding at the moment, you know, by lifelong experts in the field. So for me, that's like a very important question to answer. The other one is how can classical theory inform us about the quantum one, especially since, you know, for a decade now, I think we've been kind of arrogant in thinking that we know all there is to know about classical theories. And, you know, I think that now we realize that it's not the case. And also, I'd like to know how can we draw parallels between gauge theories and gravity to better our fundamental understanding of both of these types of theories. But in particular, I'm more keen about gravity. And with a field theory mindset, all of these questions can be and are actually addressed while doing post-Newtonian gravity. So it's not just about getting like technical results. In particular, let's just remind what is post-Newtonian gravity for those who you know, don't know just the definition. It's like the approximation where the velocity, the typical velocity of the system is very small, and we have a weak field approximation that holds. And notation is that an NPN correction is equivalent to a v to the power of 2n correction in classical gravity to Newtonian gravity. And let me highlight here that I wrote in classical gravity because for me, that's the point that I like so much about PN gravity is that we have a physical condition, and that is that the velocity is non-relativistic, but you can apply it in any of your favorite gravity theory of your choosing. So like PN theory does not, you know, favors one theory or the other. So the point is that if you get the framework, if you get how to implement the framework in one theory, then it's pretty easy to try out other candidates. So, and, you know, fortunately, beyond like doing that for us, I mean, the fact that while doing a PN precision computation, we do get answers to all of these questions that I raised. It also it so happens that PN theory actually provides the main ingredient, which is the foundation for theoretical waveforms. In particular, uniquely via the use of the effective one-body formalism that was devised by Buonanno and de Moor. in general, in this talk, I won't be giving like much of a review of EFT framework and stuff like that, because actually, very naturally, it was kind of, shown by previous speakers today. So I would like much more to kind of give you a feeling of like the status of results in the field, and like where is the frontier and what are the type of tasks and challenges that are at hand when you are getting in the thick of it. So first of all, like let's take some few minutes to take in this table. So on the horizontal axis, we have like the index n, which tells us like which order the correction enters. So it can be leading order, next to leading order, and so on and so forth. On the vertical axis, we have like growing powers of the spin. And so each NL entry enters at Pn order, which equals n plus L plus the parity of L over 2. So the parity is either 0 or 1. And L equals 0 is the non-spinning sector. So let's kind of try to get a feel by going across the boundaries of this table. So for example, L equals 0 is just the non-spinning case. And let's look at the timeline of the progress along this axis, which has been very exciting, even recently. So, starting with Newton, who gave us the universal law in back in the day. It continued with Einstein and friends in 38, giving the 1 PN correction, then Otta et al., the second PN correction, then like nowadays lifelong experts that gave us the 3PN correction, Jaranowski, Schaefer, Blanchet, Damour. And then you can see that as we progress between one correction to another, it takes the years that it takes to complete and confirm these corrections extent. So currently the state of the art is that the n equal 4 is complete, and actually pretty recently there was a very impressive accomplishments. There were very impressive accomplishments. I mean, the 5PN was approached by Fofo et al. And Blumlein et al., but very, very recently, like within the last months, actually, there have been progress in virtually fixing almost all of 5PN and 6PN by the group in like Donato Bini and Thibaut Damour and Andrea there. So very exciting and very impressive. Let's then consider the other direction. So first of all, let's see what happens when we go across the other direction, when we go vertically across the table. So first of all, we can see that, for example, if we take L equal 2, which means that we want to take all contributions that contain spin to the power of 2 into account, it means that we already have like two types of contributions there, which can be either represent either the interaction of one spin with the other, or the self-induced quadrupole, which is induced by just by the presence of spin of the object being spinning, either it's a Kelvin core or a neutron star. And as you go higher in L, this of course gets more and more complicated. You have more and more pieces that you have to complete in order to really give the complete correction in terms of order of magnitude. So let's kind of see what happened across this axis. So in general, you understand that a leading order means like 3-level type of computations. And so L equals 1 was given by Tulchev in 1959, and with equal 2 in 1975 by Barker and O'Connell. And essentially, since these are three-level derivations, the issue here is not that the computational derivation, of course, because it's very immediate. Once in a work that Jan Steinhoff and myself did, where we provided basically all the leading couplings to all spin orders, the derivation of 3-level to all orders is quite immediate. But I want to kind of draw your attention to kind of the time difference between corresponding orders with spin and without spin. So for example, you've seen that the next to leading order, um, the next to leading order correction without spin was in 38. So it took a good 20 or more years to do the next to leading order spin orbit. And so, and every time basically that an odd spin was approached, it took some time to make the leap. So that's something to note, that in general, there is a trend here where odd powers in spin are harder to handle than even powers in spin. What I note in this table also, you can see that the entries are filled with numbers. So these numbers kind of represent like one possible measure, which is the best that I found, to represent the computational difficulty that is involved in evaluating the sector. So in principle, in a sector that is to the correction to the power of n, we have the highest loop graphs that we have are n loop graphs. And I'm counting the number of n loop graphs which enter at a certain sector in a specific definition of mine of what is an n loop graph, which is different than the actual loops that you're used to seeing in QFTs, and which I will define in the following. In general, the point that I want to highlight, so first of all, you can see that, so indeed, I mean, first of all, there is no consistency in terms of computational scale. You can see that it's always like the odd powers are harder than the even powers. You can see that there is also something magical that happens in odd powers without spin in terms of some greater ease that happens there. So we can already, learn a lot by just looking at this table and seeing the trends. But definitely I want to hammer in an important message, and it's that to push the precision frontier consistently, we should push across diagonals and not do the easy thing, which we physicists of course like to do. We like to do the easy thing, and not go across axes, but really, go in there, go in the thick of it. And at the same time, I should give the disclaimer that I'm not saying that this table represents all of the state of the art, definitely not the one which is important to LIGO people, because LIGO people need a lot of results that involve radiation modes, the radiation field, and real-time results, which are not captured by the conservative sector. So definitely this disclaimer should be given. But at least, to be consistent in the accuracy that we give in the conservative sector, we should try to go across diagonals. Another thing that is important to notice in this table is that there is an area which I noted as gray area. And the gray area, interestingly, corresponds to two different things, which currently not completely clear if they are related, but one is on the classical side and one is on the quantum side. So on the classical side, it corresponds to the case where when we take the gauge condition that fixes our rotational degrees of freedom, we have a deviation from everything that worked so far in sectors below. So that's one thing. And since there is this deviation, it is not clear even classically if these sectors can be well defined, if we can get a result which is well defined. And like Radu and also Yutin in his papers, they were talking a lot about the fact that they think that classically there is no obstacle to define a higher spin to any order. To me, the answer to that is not clear, simply because I'm actually trying to compute these things one by one. And I just tackle the obstacles that come up. So on the quantum level, the gray area corresponds to the gravitational Compton scattering with spins larger than 3/2, which for gravitational interaction it doesn't mean a lot, but we know that for electromagnetic it already starts to be ill-defined. And obviously, it means that if you go deeper into 5/2, then you have a serious problem, because we have this correspondence that a classical s to the power of L, I mean, related to the types of things that you've seen since the morning, and s to the power of L corresponds to a quantum spin L/2. So for me, since for me the answer, if classical theory is able to to give predictions which are well defined for example, for s to the fifth, it's very interesting to see if we can get insight on the graviton Compton amplitude with spins larger than 2 by checking what happens at the classical level. Is it clear what happens there? I don't think so. So obviously you understood that we're avoiding to do spin. So the question is, why is spin so challenging? And basically, just like precision computation, people who don't do it, they don't understand. They don't understand why they couldn't fully understand why it's so challenging, but I'll try to kind of capture the essence of why it's so challenging. And the conceptual basic thing is that a relativistic spin, even without curved space-time, it has a minimal finite measure, and this clashes with the EFT viewpoint of a point particle, of a good localized particle. So there is no unique center, like the intuition of center of mass that we have from Newtonian physics is getting lost once we go to relativistic physics. And this puzzling issue really comes up already at the leading order correction with spin. Related to the previous points, actually, we have then accelerations that already show up at the leading order correction, and to compare it with the non-spinning case, in the non-spinning case, they appear only in the next to leading order correction. And in general, dealing with higher order time derivatives adds a lot of complexity to the computations. And again, related to that, spin is derivatively coupled, by formality. And so all related computations or integrands, they carry heavier tensorial load. And in principle, we can also have time derivatives as the derivative coupling. So it means that we get even higher order time derivative, even more higher order time derivatives. So even more complications. And on top of that, spin, when we add it, particularly beyond minimal coupling, we want to have definite parity of objects. And so it requires to deal with Levi-Civita in these dimensions. And that's a very a well-known problem from people who do high precision computation in QCD, for example. So these are, for example, the type of conceptual and computational difficulties that are involved with spin. And fortunately, again, related to my excitement today, already some amplitude groups joined the party and joined efforts in trying to figure out classical spin. So we have works by Guevara and friends, by Chung and friends, Damgaard, Auda and Bern very recently also, they shared with us their progress. So what I will do today in order to give you more of a feel is I will just really flash across some new results, which are exactly going in the thick of it into these less trivial entries in the table. In particular, I will kind of really skim across 4 results, which are the ones which appear here in both phase entries. So these are 2 3-loop results that were computed, that were published recently with Matt and Andrew, involving spin orbit, which is still, still not higher spin, but then also already progressing to a spin to the squared, which already presents also more conceptual difficulties. And also on the other hand, to see the struggle that is involved in going to higher in spin sector. So results that were computed recently with Mariana Vieira and Stavros Mogiakakos about the cubic in spin sector, and a work that will soon appear with Fei Tang from the Uppsala group on the quartic in spin sector. So again, as I said, I will definitely not review EFT, but just mention the important things, the things that are important for us to kind of notice. And these are that basically our formulation is such that we have a purely gravitational piece in our effective action, and then a piece that corresponds to the point particle action that captures the interaction of each object with gravity. And the challenge is in general to capture correctly what is this point particle action, in particular for a spinning particle. We use for example, if we're doing GR, we use like the usual action with the harmonic gauge fixing, very standard. Notice that once we're going higher in loops and we have divergences that actually come up from dimensional regularization, we should notice that we should also use a generic Newton's constant, so which is taking care of absorbing Euler unnecessary Euler constants and log pi's, which we need to kind of just kill. And then another important feature that basically was used in all of the higher PN computations using the EFT framework is the brilliant idea that basically in the non-relativistic context, one can view the time dimension as compact with respect to the spatial dimensions, and therefore it makes sense to make a Kaluza-Klein reduction over the time dimension, and that rearranges the gravitational field in terms of three new fields: a scalar one, a vector one, and a tensor one. And these are, for example, the kind of propagators that we have in our type of computation. So time and space are separated. We have a delta function for an instantaneous time interaction, and we have an integral over a spatial momentum, so d equals 3 in all our computations, which is obviously unusual in the QFT context. So let's already start to talk about topologies, because that was the kind of basic understanding that we needed to do when we went into 3-loop. And although obviously this was already tackled in the non-spinning case, we still had new insights that were not, by examining the literature very well myself, were not observed before, and are of importance for the computational aspect and also for the interpretation aspect, for the understanding of things. So basically the point is that, for example, Newtonian interaction is just represented by a tree graph. Let me explain that our graphs are such that the interaction happens between two vertical lines, which just represent the trajectories of our objects. They are not propagating. So the diagram is actually what happens in between. So these are actually the gravitons that are propagating, the lines which are finer. What we can see pretty easily is that if we just naively write the integral that corresponds to, for example, this graph, which is a two graviton exchange, we can make a change of variables, a very trivial change of variables, to make it seem like it's just a one-loop integral that is just like nested in the usual Fourier transform. So we can see that by simple change of variables, basically, and one can repeat this trick to basically to all orders. So we can basically see that we can bring all of the graphs in a certain order to a loop form, which is the maximal loop order at this G power. So that's something that was already, for example, mentioned in the paper by Colin Shear in 2013. So basically, we kind of use this analogy that that transforms all these kind of weird integrals that we do to the type of things that you like to see, QFT people like to see, and there's actual loops of 2-point functions. And that's very nice, because then we can use like all the standard multi-loop techniques that we know so well, the traditional old school one or the advanced one, by knowing like the proper master integrals and the integration by parts. Okay, now the thing is that as we continue to the topologies that appear in our order in 3-loop, then like using this change of variables, we can make all the graphs seem as 3-loop graphs on the one hand, but on the other hand, using a certain definition that I write here, we can define the loop order differently, just strictly from a kind of topological point of view. And as it turns out, it is actually important, and this is what I call the Worldline picture. So this is basically corresponds to the way that we see the graphs here. Not like the 2-point functions that I showed before. And that actually gives us, like true interpretation of the kind of things that we get in the computation, but also of the type of effects that are related with the numbers that we get, with specific features that we get. So yeah. So then specifically, let's just mention like the type of things we had to implement in order to get our three-loop results in these sectors that I mentioned. So basically, we were building on the publicly available code that Jan Steinhoff created together with me. And it's very important for me to note that in general, I want to promote sharing publicly these type of things, especially because it's relevant, it's in the service of actual experimental people. And there is actually no other, for example, PN code, which is, PN is, as I said, is such a key ingredient in predictions for LIGO. So that's like a side comment. We were generating all that was needed from this code, like extensions of this code, basically the appropriate models. And just to kind of give you an order of magnitude, like for example, in the spin orbit sector, we had a lot of graphs, as you can see. And according to my definition of what are higher rank graphs, and higher rank graphs are basically those which require a combination of a prototype of integrals that appear in the sector, we had a lot of higher rank graphs which required reduction by IBP method, which is what we did. We implemented the IBP method into the code. So there was a significant upgrade to the relevant modules of the code with just use of traditional techniques that are very familiar. In particular, our projection method, which is very, very relevant when we have spins, because you go up with the loops, and then in addition, you have the derivatives of the momenta of the coupling to spin. So we were using the projection method and a flavor of Laporta's algorithm. And in general, we were able to create a pretty efficient code that runs pretty fast on huge amount of computations. And we will actually make also this upgrade publicly available soon, as soon as we clean it up properly. Just to say, like, so what are the special features that appeared in our computation? So, like, one thing that is important to note is that well, we had zeros, but zeros already appeared systematically from certain topologies at the two-loop level. But so the interesting thing that we had here is that actually these zeros appeared like they had a coefficient, a transcendental coefficient that preceded them. And so then when they were, these type of prototype integrals actually appeared in graphs that required IBPs. And as anyone who has done IBP know that IBP has poles in it. What happened is that the poles cancel these zeros, and this way the transcendental numbers were revealed. So actually we really traced back the transcendental number to a very specific topologies, and also with a certain physical interpretation through the graph. And the other thing that we had, which was of course new to this feature, so one thing that is new to these sectors is that we had transcendental numbers. And the other thing is that we had simple poles in the dimensional regularization parameter and logarithms, but those essentially drop from observable quantities, so we shouldn't be worried about them. Now, just to add that in principle, when we went into higher spin, to the higher spin sector, that already required beyond the computational thing also to extend the operators in our actions. So, to check if there are other contributions, and actually we do this systematically following symmetry, the same kind of symmetry considerations and power counting that were outlined in the original formulation paper that gave all the linear in curvature couplings to all spin. And it actually turns out that there are two operators that contribute to the sector, but from their form, we can see that they enter in a topology that is below the topology that we handle this paper. So we'll have to keep this in mind, but it was not relevant to the result here. So just to give you an impression of what the result, for example, of the spins quadratic in spin looks like, I just want to draw your attention that there are, as you can see, different pieces that contribute. And we have to take all of them into account on an equal footing. So like S1 to S2, and then a non-linear interaction just of spin with itself, but also an interaction which of the spin-induced quadrupole, which is different than a nonlinear interaction of a spin with itself. So this is the type of result that we get. I'll just briefly show, like, talk about in spin in the sense that it was similar to the type of things that we already computed in lower order sectors, where we take into account basically all the combinations of higher spin multiples that contribute to this order. So this was kind of it's a one loop thing. There is no big computational difficulty, but that's where things start to get weird. Is that actually we get kind of weird contributions because of the fact that I was mentioning that when we get to this order, actually we cannot gauge the spin in the very simple way that we did in previous sectors, and we get it. So eventually, at the final rule level and also at the graph level, we get kind of a graphs that basically you could represent as kind of basically mixing two multiples together. So, like we can kind of make the analogy between elementary spin multiples, and then we get in practice contributions from composite multiples. So, and then finally, very soon you'll see the work with Faye from Uppsala, where we pushed it further. And again, this goes to show that the issue here was definitely not the computational, strictly like loop computational difficulty, because in general, I told you that even in spin sectors are easier, and that these are the type of nonlinear graphs that we had to compute. They're very straightforward. It's not a big deal to compute it in general. But here, even weirder things happen. There is like much more mixture of multiples, like even to the extent that we have now non-minimal coupling multiples mixing, so product of Wilson coefficients, and on top of it, and whatnot, and on top of it, we have like relevant operators now entering in quadratic in the curvature. So that's a lot of things to handle. But all of this already comes into to the next to leading order quartic in spin sector. So I find it challenging. So I definitely don't, I'm not sure that to go one order higher would be trivial. So let me just conclude by giving my kind of outlook to the situation, to the current situation, like, as a consequence of my own work on it, is that in principle, we have real world scalability. We actually, by approaching these four sectors, we basically pushed the precision frontier to 4.5 and 5 PN orders, respectively. So everything with spin is basically touched at this order of accuracy. We have a framework which is completely self-contained. It's not dependent in any other methodologies, and it's able, in principle, to be pushed forward. And also, we make sure to share, to publicly share the computational tools that we develop along the way in order to carry these things out and to share the results with everyone. So that's kind of the real-world aspect of it. And the actual fundamental aspect of it that is very, very troubling to me, at least, is that, well, it seems like we have already some kind of a feeling that the new features in next to leading order higher spin sectors, they resonate with some kind of a picture of a composite particle, which corresponds to what we have in the quantum case, in the higher quantum spins. And going into the gray area that I showed in the table becomes extremely intricate, also classically. That's my conclusion. And maybe we can, if we will try to push it, see if there is a breakdown, and if so, where and why, and does it give us insight on the graviton-Compton amplitude with higher spin, with spin larger than 2? And finally, I want to ask the amplitudes people and everyone who came up so bravely recently with all these magnificent approaches to tackle spin from amplitudes, if they can try to help to capture such classical effects, even those which were already captured at this level. So I will end now, and thank you all by saying that I would like to meet each and one of you in real life next year in Amplitudes 2021, which will happen in Copenhagen. So thank you all.
All right, thanks, Michelle. Well, let's give her a virtual round of applause and open up the floor to questions. Looks like there's one from David Broadhurst.
So congratulations on handling the tensorial, spinorial, combinatorial complexity of this problem. I'm struggling to understand its analytic complexity. You said at one stage that essentially your integrals reduce to two-point functions, single-scale integrals within epsilon of 3 dimensions. But if you go to sufficiently many loops, I expect to see interesting numbers, and all those interesting numbers disappear from your final results.
Yeah.
So did you encounter them at intermediate stages, and what were those numbers at intermediate stages which magically disappear from the answer?
Yeah, well, I should admittedly, I admit my sins. The things I compute are not physical. I'm computing a Lagrangian to begin with, an effective action, which I will later, I'm computing a heavy object, but from which I can basically derive a whole host of gauge invariant quantities of my wish. And the way I constructed it is such that I can straightforwardly derive the physical observables. So again, you can ease your worry by knowing that what I'm computing is to begin with not physical. So it's okay to have that. So basically, for example, for the poles that I get, I can make a coordinate redefinition, and the coordinate is a gauge, and remove them.
If I might jump in, I think David's asking whether we got anything more than Riemann zeta values, and the answer is no. Not at this level.
That stays physically? Yeah, physically it's only the transcendental factors which are new. Yeah.
Thank you for that clarification.
Sorry.
Chashan had a question.
Thanks, Michelle, for the nice talk. So I have two questions. So maybe you could clarify the very end of your talk, saying that whether amplitude could capture what classical effect. Maybe you can clarify the last comment in your talk.
The last comment in my talk, which one? These ones.
Yeah, like can amplitude approach? What do you have in mind for like such classical effects?
For example, like next to leading order, quartic in spin, but not only like in a certain limited gauge invariant quantity, but something, like something that gives me much more information. Or maybe several gauge invariant quantities, as much as possible. But also the higher loop that I showed, for example. I mean, all the sectors basically that I showed.
Do you mean like a conceptual abstraction, or you just mean like technical? We haven't gone into there yet. It's just
sorry.
Do you mean capture by capture here? Do you mean like conceptual abstraction, or you mean just we haven't gone to that far yet?
I don't know. You tell me. Well, your frameworks are are in their birth, and then we should see what you get.
Okay. Sorry.
I mean, because that's the thing. I mean, you deriving like tree-level results and stuff like that is kind of, usually you get agreement on these type of things. So the challenge is to to see that we all agree on things which are less straightforward.
Yeah, I have a second question. So I'm not sure if you mentioned this in your talk. So for example, in your recent paper with Sam and Andrew, you show that there's a IR divergence at G to the fourth order.
I showed that there is
the IR divergence, one over epsilon divergence.
Yeah.
So I wonder if you have a feeling whether that's an actual divergence as in the tail turn, or you expect that still a gauge dependent part that will cancel once you calculate the full potential, the higher order it be.
So that's what I answered to David, I think it was before, is that it's the result that I get is a potential, which is obviously a gauge dependent thing. And actually, even if you compute from it the equations of motion, which are still coordinate dependent, like the poles are, you can remove them, but the logs survive. But once you actually compute something which is completely observable, like for example, the binding energy, then also the logs drop. So basically these things drop, but the nice thing is that obviously the appearance of these things shows you, I hope it showed you that this is the places where the computation gets nastier in general.
Right.
So now we also know where to find, like, to which topologies it corresponds, you know, in the worldline picture, for example.
Yeah, sorry, let me clarify my question. So my question is more like in the scalar part, we know the tail effect only appear at G to the fourth V square order. The G to the fourth static part doesn't have the tail effect. So I was just curious about whether that's still the case in spin, or you expect even for the stationary return, you already will get the tail effect.
I have to say I don't understand. I don't understand what you say.
Oh, I just mean in the scalar part, the tail effect comes in that 4pn.
Yeah.
It doesn't come in at G to the fourth, V to the zero order. But somehow in your spin calculation, you do see this IR divergence. So I wonder if
sorry, now I understand what you're asking.
Right.
I think I do. You're saying like, well, it's a funny thing that they drop out of like the non-spinning sector.
Yes.
That's what you were asking?
Yes, it doesn't
Yes.
appear in the non-spinning.
Yeah, so that's actually a very curious thing that I'm also interested in knowing the answer to, and that it seems like in the even sectors in spin, there is like this magical cancellation, even at the gauge dependent level of all like redundant, you know, unphysical stuff. And in the even powers, they stay. So it also, this magical cancellation also happens in the spin, in the quadratic in spin sector that I just showed you the result. There were no poles and logs there.
Okay,
But
thank you.
like I don't have a very good explanation on why they drop out from some and stay in others.
Thank you.
So we've got two more questions. We're running over time, so if we can get through them a little quicker, maybe. But Enrico, you had a question?
Yeah, can I ask one quick question? So can you learn something from QCD when you consider heavy mesons that can have, in principle, higher spin effects? Has there anything been computed in the QCD literature, like heavy quark physics, that you can then take to?
I think actually, if Kais is online now, I think he's the one who is the most authoritative to answer this, because that's kind of the approach that they took in their work. Kais and Andreas, if they're online, of this heavy particle effective theory. I myself honestly can't answer your question because I just don't know enough about the QCD computations.
Okay, and then we had a
Sorry.
question from Nima.
That's really a comment, and it's related to the previous question as well. I mean, obviously, what's we can't have. We don't have point-like elementary particles with high spin, and B, of course, in the present context, they're definitely not point-like. They're big, fat black holes. So what happens in other contexts, like QCD or the hydrogen atom, millions of simple examples where we have bound states composite objects, is that you can begin to systematically take the excitations of the particle into account. And in the gravitational context, those are the quasi-normal modes. I mean, that's obviously what's missing when you talk about the Compton scattering, is that there is this effect where the black hole actually absorbs a thing that's coming in, excites a quasi-normal mode, and it decays back out. So we have to sort of include these unstable particles, if you like.
Okay, so like additional internal degrees of freedom.
Right. And I'm just wondering, but that's sort of very standard in GR to think about the quasi-normal modes. And so it seems like that thinking about those excitations, that they have to be included in the story in order to go further. Right.
Yeah, we can complement our EFT description by additional degrees of freedom. I mean, it seems that's basically signaling the fact that our EFT is not complete at this point. And so maybe, but who knows? I mean, we should do it, and then we will know.
All right. With that, let's thank Michele again.